Alrighty, we're going to try the practice test answers here. So, number one, consider the vaporization of ethanol which boils at 78. Here's an equation. We're going from liquid to gas, and the energy is on the left, which means that it's endothermic. A 50 milliliter sample of ethanol is placed in an empty, isolated container at 30 degrees. How does the temperature change in this process? So the idea here is that if we had a container, okay, with some ethanol, well, some of this is going to turn into vapor, okay, and as that stuff turns into vapor, it absorbs energy. So what's going to happen is that the ethanol is going to get colder and colder and colder. So the temperature will decrease. What's this? Temperature will decrease as the kinetic energy of the molecules is used to break attractions. This is exactly your number one. A. The temperature is going to decrease, and you know this is that something evaporates like off your skin. It cools you down, because as these attractions between the molecules are broken, then it absorbs energy. Okay, you can take this and the temperature will increase, and that's not good. The temperature will increase, no. The temperature will remain the same, no. Okay, the temperature of the alcohol is going to decrease. Number two, a 50 gram piece of aluminum is placed in an insulated container with 50 grams of acetone. What is the temperature of the mixture after thermal equilibrium is reached? So what's happening here, we're talking about a warm object and a cold liquid, and one's going to give off energy, one's going to take in energy. So we have Q equals mc delta T, okay, and we have another Q equals mc delta T. Now, let's just think about the question first. So one of these is for the aluminum, okay, and one of these is for the acetone. And we can look at the problem here that the 50 gram piece of aluminum is at 50 degrees, and the 50 grams of acetone is at 20 degrees. So, okay, we have 50 degrees, 20 degrees. Okay, then we know that the answer is going to be somewhere right in between those two. Okay, right in between 50 and 20, that's a 30 difference, so 20, 30, about 35. Now that would be if both of those substances were equally good at absorbing and releasing heat, the same specific heat, but they're not. Okay, the aluminum is only 0.9, okay, and the acetone's 2.5, so it's going to be much, much closer to the acetone side. Okay, so it's going to be higher than 20, okay, but not nearly up to 35. Okay, so it's going to be between 20 and 30, between 30 and 40, certainly not between 40 and 50, higher than 50. So we know the answer here is going to be between 20 and 30. Now you can go back and calculate the whole thing. Okay, you take Q equals mc delta T, Q equals mc delta T. Put in the masses for both, put in the specific heats for both. And remember, for the T's would be X minus 50 degrees, and this one here would be X minus 20 degrees. And then you can calculate and find out that it is going to be between 20 and 30. But you don't need to. Okay, for number three, which of the following best describes the energy change in the reaction? Now, this kind of a problem, okay, it says which best describes the energy change. The reaction is endothermic, the reaction is endothermic, exothermic, exothermic. Okay, so here's the energy way over here. So since it's on the right, it's giving off energy, we know that it is exothermic. So we can knock off those two answers right away. Now, endothermic because the total bond energy of the reactants and the bond energy. Okay, we're talking about bond energies, so we have to go back to a delta H picture, and the idea if it's releasing energy, that means it's starting high and going low. But bond energy is how much energy it takes right here, how much energy from the reactants to separate atoms, and the bond energy of the products, is this guy. So the bond energy of the products is going to be larger than the bond energy of the reactants. So let's see if we see that answer. The reaction is exothermic because the total bond energy of the products is greater than the total bond energy of the reactants. This is the situation, and remember, bond energy is this part right here. Number 4, consider the heats of combustion below. What is the value of the delta H of reaction for the process below? Well, okay, so we have heats of combustion. Now, combustion, implies the reaction that we have C2H5OH and add oxygen to it, and it turns into CO2 and H2O. And for the methane, okay, CH4 plus O2 turns into CO2 and H2O. Now we could write out the Fisher, we could balance and all that, but we know just to look at what we're trying to do, I want to get those two chemicals in the right place, and so you can see what's going to happen is that this guy is going to have to get turned around, okay, because I want the methane on the right, and I need two of them. So this one's going to be flipped around and multiplied by 2. So from that much here, I can see, well, I'm going to need negative 1400, okay, kilojoules per mole. And that's going to be because I have one of these and it is on the correct side. And for this other side, okay, I'm going to use negative 900. Okay, but because I turned it around, I make it positive 900. And because I have to have 2 moles of that, then it's going to be positive 1800 kilojoules per mole. So here are my two numbers, positive 1800, negative 1400. So they're different by 400, and it's going to be a positive value. So my final answer here is positive 400, answer B. Okay, number 5, which of the following processes will result in the greatest increase in entropy? So the first thing we'll look for is like gas solid going to gas. Here's 2 gases going to 1 gas. Okay, that's not a good, that's going to be less entropy. Gas, 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 and liquid. So we have 1, 2, 3, 4, 5, 6 moles of gas turning into 3 moles of gas in a liquid. That's no good. Here we have a gas and a gas, 2 moles of gas turning into 2 moles of gas, so there's no real increase there. Here we have solid going to gas. That's the best answer right there. So we're increasing the number of moles of gas. That's an increase in entropy. Okay, number 6. Consider the following process. The value of delta S for the process is 165. Over what temperature range is the process thermodynamically favorable? Okay, well, we can see here that with the delta H is 55 kilojoules, and here we're saying that the delta S is 165 kilojoules. Okay, and both of these are positive values. Okay, because energy on the left side is positive. So if delta H and delta S are positive, then we know that this is going to be thermodynamically favorable at higher temperatures. Okay, now, so temperatures above 333, temperatures below 333, all temperatures, no temperatures. Okay, well, the fact that they're both positive, okay, delta S, that's good, delta H, that's not good, so it's not going to be good at all temperatures, and not at no temperatures. We can find something. Okay, and since we were looking for a high temperature, then we're really looking for the one above 333. Now we could go back and calculate exactly what that's going to be. Okay, and we're going to have to use, delta G equals delta H minus T delta S. And we're looking for that temperature at which it switches over from spontaneous to non-spontaneous or vice versa. So this can be a 0. So 0 equals delta H minus T delta S. Or we could say that delta T delta S is equal to delta H. And we want to get T, so we'll divide both sides by delta S. So we can take these two values and put them in. Notice that this is 165 joules and this is 55 kilojoules. We would have to switch our values here. So we'd use 55 on top. We'd use 0.165 on the bottom. Okay, and we're going to get a value like 333. But we can tell anyway without it is that's going to be something above the 333 Kelvin. Number 7, which of the following, given the following reduction potentials, a galvanic cell is constructed with aluminum in aluminum solution, zinc in zinc solution, which of the following would be observed? Well, before we do this, we really want to stop and say, okay, what is our overall reaction? So which one has the larger value? This is the larger value. It's the less negative, the larger value. So what's going to happen is that the zinc ion is going to be reacting with the aluminum metal, and it's going to be turning into aluminum ions and zinc metal. And it's 2 and 3, so we're going to have to multiply. So this is going to be 3 of these and 3 of these and 2 of these and 2 of these. So there's our overall reaction. So as this reaction starts to occur, okay, we're going to use up some of our zinc ions. We're going to make some aluminum ions, and the aluminum metal is going to go away, and the zinc metal is going to be formed. So the mass of both electrodes will increase. No, this mass is going to get less, and this mass is going to get larger. So that's not A. The mass of neither will change. No. The mass of the aluminum electrode will decrease while the mass of the zinc electrode will increase. That is the answer. And again, the idea is, get the overall reaction before you think about the question. Number 8. Okay, given the following reduction potentials, beaker A contains, as a solution, beaker B contains a zinc solution. When a piece of copper is placed in each beaker, in which beaker will a reaction be observed? Okay, so we're talking about copper. Now these are, let's check, okay, these are in the correct order, okay, from highest to lowest. So that means something in the upper left would react with something in the lower right. So we're talking about a piece of copper metal. So copper metal would react with a silver solution. Okay, it would not react with a zinc solution. That's not going to happen. And it wouldn't react with a copper solution. So we're looking for copper mixing with silver. And that would be beaker A, silver solution with the copper metal. And that's the only one that's going to happen. So that's going to be answer A, beaker A. Number 9, a galvanic cell based on the reaction above is set up. What's the potential of the cell if silver is 0.5 and copper is 0.5? So here's our reaction. And if we want to figure out about, what's the cell potential, then we need to look at Q. Okay, now Q, remember, is just the equilibrium expression. And so it's going to be copper ion concentration divided by silver ion, products over reactants. And silver is squared, so this is going to be 0.5 over 0.5 squared, which is going to come out to be 2, because 0.5 cancels, 1 over 0.5, which has a value of 2. Well, if we had a standard cell where everybody was 1 molar, so a standard cell would have a value of 1. So this is larger than 1, larger than 1. And what we learned before is that the KEQ for a cell that works is very, very, very large. So the KEQ is very large. So here's 1, when the standard cell, and this is 2, so that means that this Q is closer to KEQ, and as the reaction, as the cell runs, the voltage is going to get less and less and less and less. So we expect to get a voltage that's a little bit less than 0.46 because Q is closer to KEQ. So we have a value like that. It's not going to be 0, not until it's dead, and it's not nearly dead. Less than 0.46 but not equal to 0, that looks like our answer. Equal to 0.46, no. And greater than they're certainly not. So because our Q is greater than 1, then we know it's closer to KEQ, and the voltage is less than 0.46. Answer B. Now we go to number 10. How many grams of chromium metal is deposited when a 10 amp current runs in a 1.5 molar chromium chloride solution for 16 minutes? Well, the key piece here, is 16 minutes. We'll start with that. And the 10 amps means we're going to get 10 coulombs per second. So let's start here. So I got 16 minutes. And I know that 1 minute is 60 seconds. And I know that for every 1 second I get 10 coulombs of charge. And I know that 48,500 coulombs is 1 mole of electrons. That's my Faraday constant. I should have said this is 98,400. This is bad. 98,400 and 96,000. Okay, 96,485 coulombs for 1 mole of electrons. Okay. Chromium, okay, we can tell by the compound that that's a 2+ solution. So we have 2 moles of electrons for every 1 mole of chromium that's forming. And we're trying to get grams of chromium. So 1 mole of chromium is, I believe that's 52 grams of chromium. Phew. Okay, so I'm going to work out this answer. And for this, I get an answer of 2.586, okay, grams, which is pretty close here to the 2.6 if we round off to 2 significant digits. Okay, so 2.586 grams of chromium. And it's a little bit messy, but you can kind of follow my math on that. Okay, number 11. An electron in a hydrogen atom changes its vibration from 3d to 1s orbital. The energy from this transition would be observed would be what? Okay, so we're going to go, okay, 3d to 1s. So remember that how hydrogen goes. There's the n equals 1, there's n equals 2, n equals 3, n equals 4. They get closer and closer and closer. Okay. And we're talking to going from 3 down to 1. And so since it's dropping down, it's going to give off some energy, so it's going to emit. So we can lock off the absorption. Okay, well, what's going to happen? The ones that give off visible light, like red, that is 3 down to 2. Okay, everything that drops to 2 is the ones that we can see, 3 to 2, 4 to 2, 5 to 2, 6 to 2. So that's not the answer. It's going to be UV. Everything that drops to 1, that is much larger than we can see because of the spacing. So that's higher energy than we can see, so that's going to be giving off UV light. Answer C. Okay, how many electrons in the ground state of phosphorus have m sub L equal to 0? Well, there we have to remember about our quantum numbers. Remember quantum numbers N, L, m sub L, and there's also spin, but that doesn't really count at this point. So how many have m sub L equal to 0? Well, if we were doing phosphorus, okay, we say, well, phosphorus is, 1s2, 2s2, 2p6, 3s2, 3p6. I'm sorry, 3p3. Okay, and if we fill them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, this is phosphorus. Well, who has m sub L 0? Okay, remember that s orbitals have a value here of 0 for L, and m sub L can be anywhere from negative L to positive L. That means anytime you have an s orbital, that is going to have a m sub L of 0. So there's 6 electrons right there. Then when we get to the p orbitals, okay, p orbitals are when L is equal to 1, which means m sub L could be negative 1, 0, or positive 1. So of these 3 orbitals, one would have m sub L of negative 1, one would be 0, one would be positive 1. So we say here I have 2 more electrons, and here I have 1 more electron. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of these electrons would have quantum number m sub L with a value of 0. Now phosphorus, this is a good one to ask for this kind of question because, it's 1, 2, 3. If I did something with only 2 electrons in those p orbitals, then the answer would be more ambiguous because you don't know, would there be one in the orbital that's considered 0, blah, blah, blah. Okay, but for this atom, okay, this is perfect kind of a question. So 9 of them have m sub L equal to 0. Okay, number 13. Okay, we'll look at this and say, okay, how many electrons are unpaired in the ground state configuration of iridium? Okay, so iridium, how many electrons are unpaired? Well, if we look at iridium on the periodic table, okay, we're going to find it's kind of down in the d orbitals. Okay, it's number 77. Okay, it's in the d orbitals, and if you count up the d orbitals, 1, 2, 3, 4, 5, 6, there are 7 electrons in the d orbitals. Now, we don't have to worry about anybody besides the d orbitals because this is 3, 4, 5d, because everybody else is going to be paired up. So, nothing else could be unpaired. So if we're looking for unpaired, we have 7 electrons in the d orbital just from where it is on the periodic table. So that means we're going to have 3 unpaired electrons. And that's all the thinking we have to do about that. We only care about those last electrons being filled in because those are the only ones that will be unpaired. Okay, here's an element, okay, from the PES spectrum. So we know that this is the 1s, we know this is the 2s, we know this is the 2p, just from their positions. And in an s orbital, we know it can only hold 2, so that size of a peak must mean 2, and since these are the same size peak, that must be 2 and that must be 2. So the electron configurations 1s2, 2s2, 2p2, that's 6 electrons, that is carbon. And that's all there is to that question. Okay, 4.15. How does the ionization energy of beryllium compare to that of boron? Okay, beryllium and boron. So now if we look on the periodic table, we say, you know, we have lithium, we got beryllium, we got boron, okay, then we get carbon, nitrogen, like that. So if we were filling these up in their orbitals, we can see what's going to happen. Beryllium is 1, 2, 3, and 4. So we're talking about ionization energy it takes to pull off that electron. Okay, for boron, okay, it would be 1, 2, 3, 4, 5. Okay, so we're pulling off that electron. So how much energy it take to pull that electron versus this one? And what's different, this is coming from a 2p orbital, and this is coming from a 2s orbital. So it's going to turn out that the boron, even though it has more protons, and you would think it'd be harder to pull off its electron, it's not, because it's coming from a higher energy orbital, the 2p versus the 2s. And because it's coming from a higher energy orbital, it takes a little bit less energy to remove that electron. So the ionization energy of beryllium is higher than that of boron. Okay, so we have boron's easier to pull off than you would think, so that's good. Because it's higher than boron, because the outer electron of boron occupies a higher energy orbital. Boron comes from a higher energy orbital. That's the answer right there, B. Now, on some of the people that got this test, we had a typo here, and it said beryllium here, and it's supposed to be boron. So if that's the right, otherwise there was no correct answer. So, but that's the situation. The boron electron is coming from higher energy orbital, so it's a little bit lower. So beryllium is higher than boron. Answer A. 16. Which of the following is expected to have the highest melting point temperature? Well, if you look at these are all ionic compounds. So if it's ionic compounds, then we're talking about Coulomb's law, charge over distance. So Q1, Q2 over d squared. And we can see that calcium, this is a 2+ ion and a 2- ion. Cesium and iodine, that's +1 and -1. Magnesium and oxide, 2+ and 2-. And Na and F, that's plus and -1. So who has the highest melting point? Who's got the strongest, attraction between them? Well, it's not going to be these +1, -1s. It's going to be the +2, -2s. It's going to be like 4 times stronger. And it's going to be the smaller they are, the better. Okay, and MgO is smaller than CaS. Okay, because they're higher up in the periodic table. So the distance between those ion centers is smaller. That's going to be a much stronger attraction because it's Q1, Q2 divided by d squared. Okay. 17. What's the bond order of S in SO2? Well, SO2, we say, well, what does that look like? It's going to look something like this. And so what we have is we have 2 resonance structures. And when you have 2 resonance structures, the bond order is 1.5. It's 3 pairs of electrons, so that, the question is, how many pairs of electrons are holding these together? We have 3 pairs of electrons over 2 situations. Okay, so that's 3 divided by 2, that's a bond order of 1.5. If we had 3 resonance structures, it'd be 1.33. And remember, the other thing is that a single bond is 1, a double bond is 2, and this is, somewhere between those two, it's 1.5. Okay, which of the following has the smallest bond angles? Okay, so we have to kind of look at these structures here real quick. So BCl3, boron can make 3 bonds. Okay, so that's going to be 120 degrees. I'm not doing all the lone pairs. ICl3, okay, so I has 7 valence electrons. It's going to take 3 of them to hook on my chlorines, and that means I have 4 left. So that is going to be a steric number 5, trigonal bipyramidal, and the 2 lone pairs will be around the middle. So it's going to be trigonal bipyramidal like this. I get a lone pair, I get a lone pair, so my atoms are here, 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 and here. Okay, so my bond angle is going to be 90 degrees. That looks pretty small. NCl3, okay, NCl3, nitrogen, okay, has 3 bonds it can do. So 1, 2, and 3. And they can do the rest here. Okay, so those are going to be a little bit smaller than 109. Okay, but you know, I'll pretty much say 109, 108, 107, but I'm going to say 109 degrees, 109.5. The lone pair squishes them a little bit closer, but that's an easy number. And PCl3, exactly the same thing. Okay, PCl3, because I have that lone pair on there, so that's not my answer either. So again, that's going to be roughly 109, okay, 90, and 120, so this is my answer, ICl3, okay, 90 degree bond angles. 19, which has a higher melting point, CF4 or SF4? Okay, well, CF4, carbon can make 4 bonds with the fluorines. That's going to end up being, tetrahedral, so it's going to be LDFs holding this together. And SF4, sulfur has 6 valence electrons, so it can make 4 bonds with the fluorines. But we also have a lone pair on there, so that's going to make it a little bit off-center, and it's going to have DDI as our intermolecular forces. So that's going to be a little bit stronger. So which has a higher melting point, CF4 or SF4? CF4, no. CF4, no. SF4, because it is polar, it has dipole-dipole interactions, while CF4 is nonpolar and has London. That's exactly the answer. Okay, number 20, consider this compound. How many sigma and pi's? Okay, a single bond is a sigma. Okay, so here's a sigma, and a sigma. And then the double bond's going to have a couple of pi's. So we're ending up with 1, 2, 3 sigmas and 1, 2, 3, 4 pi's. So a triple bond is a sigma and 2 pi's, single bond's a sigma, and that's the answer. The following observations were made of a crystalline solid. It melts very high, does not conduct electricity, and dissolves in water. That's critical. Okay, so who dissolves in water? Ionic compounds dissolve in water. So pewter, okay, silica, that's quartz. That's not going to dissolve in water. Carbon dioxide dissolves in water, but that's a gas. It does not melt at 12 in there, so that's not the answer. So it's magnesium oxide, nice ionic compound. Okay, which of the following is expected to have the lowest melting point temperature? So if we're talking about pure substances, we want to look at LDFs. Okay, so intermolecular forces, so that's LDF. Okay, H2S, that's going to be slightly dipole-dipole. Okay, HBr, that would be a dipole-dipole, and LDFs would actually be pretty important in that. NH3, that's going to have hydrogen bonding. Okay, so the lowest melting point is CH4. In fact, that's a gas. Consider the diagram shown, at which point indicates the normal melting point. Okay, so this is gas, this is liquid, this is solid. So somewhere along this line at 1 atmosphere pressure, so that's the value there. Answer B is when it will melt at 1 atmosphere. Okay, 24. The following graph shows the vapor pressure of water as a function of temperature. A 50 milliliter sample is placed in an empty container. Which of the following would be observed over time? Okay. So we're going to say here at 60 degrees, we want to look up, and we're going to see that that looks like it's about 150 millimeters of mercury. So what's going to happen is that the volume of the liquid is going to decrease as stuff evaporates, but it's only going to evaporate until the pressure gets to 150, and it's going to stay there. So it's answer B. Okay, the sample contains a mole of helium and a mole of neon. Okay, which is going to be greater for helium? Okay, helium is a lighter gas, it's less mass, so it's going to be faster. And the last thing here is which conditions will something act most ideally? Okay, most ideally we want high temperature and we want low pressure. Okay, high temperature and low pressure. That looks like answer C, and that's it.